Today I'll be taking you guys through part 3 of our Algebra and Functions unit, Quadratic Functions. Today's quote is from William Paul Thurston, a math professor and Fields Medal awardee from Washington, D.C. The Fields Medal is one of the highest honors a mathematician can receive. Thurston says, "Mathematics is not about numbers, equations, computations, or algorithms. It is about understanding." Quadratic functions have a few important characteristics for us to note. First, the shape of the quadratic function is a parabola, or a U-shaped curve. The general form of a quadratic function is the following: fx equals ax squared plus bx plus c, where the value of a is not equal to 0. The vertex, which is the highest or lowest point of the parabola, depending on whether it faces up or down, is negative b over 2a, comma f of negative b over 2a. Here, f of negative b over 2a means the y value when x equals negative b over 2a. Parabolas also have an axis of symmetry, which is basically the line that you can fold the parabola over to perfectly overlap with the other side. The axis of symmetry is a vertical line passing through the vertex, and its equation is x equals negative b over 2a. Finally, we have vertex form. Similar to the slope-intercept form and point-slope form of linear functions, quadratic functions can also be expressed in vertex form. You can use this form if you know the vertex. If the vertex is h, k, for example, the parabola can be written in vertex form as y equals a times x minus h squared plus k. Going back, the reason why the x-coordinate of the vertex is negative b over 2a is because when we express f of x equals ax squared plus bx plus c in vertex form, the h is equal to negative b over 2a. Try this yourself to see if you get the same answer. Moving on to our first example, let's try graphing the quadratic function y equals x squared and connect those points to draw the graph. First, if x equals 1, y will equal 1 squared equals 1. If x equals 2, y will equal 2 squared, or 4. If x equals 3, y will equal 3 squared, or 9. And we can mark those points on the coordinate plane and connect those points to draw the graph. Making a table of values can get tedious, however, especially if the numbers are very large or very small. Sometimes they don't even turn out to be integers. That's why we have a series of steps to graphing that can help us be more efficient when drawing the graphs of quadratic functions. First, we need to find the vertex and axis of symmetry. This might already be given in the problem. If not, you might have to use the information you have to express the parabola in vertex form. Second, find the x-intercepts. Some graphs won't have x-intercepts. However, if they're up top over here like this, or facing down over here, then we have to move on to the third step, which is find the y-intercept. The y-intercept is the point where the parabola crosses the y-axis. To find the y-intercept, plug x equals 0 into the equation. The final step now is to connect the dots. Look at the coefficient of x squared to see if it's bigger than or smaller than 0. If it's bigger than 0, the graph will face up, like it does here, since the coefficient of x squared is equal to 1, which is greater than 0. However, if the coefficient of x squared is smaller than 0, the graph will face down. Next, we have a very important formula that you'll be using very often throughout your high school math career, the quadratic formula. If we're given the quadratic function, we can use the quadratic formula to figure out the x-intercepts, or zeros, of the function. Sometimes the stuff inside the roots, b squared minus 4ac, will be less than 0. In that case, the function has no zeros, like we mentioned is possible in the previous slide. If b squared minus 4ac is bigger than 0, the graph will have two different x-intercepts. If it's equal to 0, then the graph will have one x-intercept. Imagine the function in that case as briefly touching the x-axis, then bouncing back. Y equals x squared is one example of a quadratic function that touches the x-axis and has 1 0. Now let's say you use the quadratic formula and arrived at two zeros, x equals a and x equals b. Then the equation will be x minus a times x minus b equals x squared minus a plus bx plus ab, and you can use the FOIL method to get here. Here we have some useful equations that we'll briefly mention but won't be going into yet. Given two zeros, x equals a and x equals b, the sum of the zeros is equal to negative b over a, and the product of the zeros is equal to c over a. Now let's try using the formula on an actual function. Here we have y equals 3x squared plus 2x plus 15. We know that a equals 3, b equals 2, and c equals 15. We'll plug these values into the quadratic formula to get x equals negative b or negative 2 plus minus b squared minus 4ac, or 2 squared minus 4 times 3 times 15 over 2a, or 2 times 2. And that's how you find the zeros of this function. Now let's move on to our exercises. Graph f of x equals 2x squared plus 4x minus 1. Here we'll group the x squared and x terms together. And we also note that a equals 2, b equals 4, and c equals negative 1. So when we group the x squared and x terms, we get 2x squared plus 4x minus 1 equals 2 times x squared plus 2x minus 1. Next, we'll complete the square. This means figuring out which value we need to add here to make this a perfect square. We know that the only possible value is 1, which will create x plus 1 squared, or x squared plus 2x plus 1. Then we have to make sure to subtract 1 again to cancel out the 1 that we just added, and that's because the 1 wasn't there in the first place. Since we haven't touched c, or negative 1 at all, that stays at the back here. And moving this part out of the parentheses, we get 2 times x squared plus 2x plus 1 minus 2 times 1 minus 1, which equals 2 times x plus 1 squared minus 3. Then the vertex will be equal to negative 1 comma negative 3, and the axis of symmetry will be x equals negative b over 2a equals negative 4 over 2 times 2 equals negative 4 over 4 equals negative 1. To find the y-intercept, we plug in x equals 0. Then the y-intercept will be 2 times 0 squared plus 4 times 0 minus 1 equals negative 1. Now we can finish drawing the graph based on this information. And since the coefficient of x squared, or the a value, is bigger than 0, the graph will face upwards. And we can connect the dots to draw a graph like below. Finally, for our last exercise, we'll be finding the sum of the zeros of 2x squared minus 4x minus 3. We mentioned the sum of zeros formula briefly, and it was negative b over a. Here, a equals 2 and b equals negative 4. Plugging those values in, we get negative b over a equals negative 4 over 2 equals 2. So the sum of the zeros of this function is 2. And that's it. Thank you as always for your attention, and we hope this helped. Next class, we'll be moving on to part 4, which will involve higher degree polynomial functions. Goodbye.